and the event algebra A, histories and events. I'll usually probably call these by Greek letters, and the events by capital Roman letters. Now, where does the dynamics come in? So from the quantum point of view, from the classical point of view, the dynamics is given by what's called the probability measure on the sample space. But let me not dwell on that. But from the quantum point of view, it's given by something which is mathematically speaking very similar. From this point of view, quantum mechanics is almost, as Ball said, not quite as Ball said. He said, I think, a non-commutative probability theory. I would say it's a generalized probability theory that incorporates interference. That would be the history's way of thinking about it. So it's some sort of generalization.
This algebra is commutative, no?
Well, there's no algebra, forget it. We'll come back to that. We just said, yeah, this algebra is commutative. Boolean algebra. Boolean, it's an algebra over Z2. It's completely, yeah, it's a commutative algebra, absolutely. Yeah, this algebra is commutative, yeah. And in fact, a Boolean algebra is no more than an algebra which is idempotent. So it's an algebra such that every element squares to itself. I think that's a necessary and sufficient condition for being a Boolean algebra. From this you can derive the commutativity and so on.
What is it? What are you saying?
A squared equals A.
0, 1. Huh? 0, 1.
Well, the eigenvectors would be 0, 1, but the...
It's over Z2, so it has to be like that.
No.
You said the coefficients are Z2, no?
The coefficients are Z2, but that doesn't imply that A squared equals A.
Oh, I see. A squared equal to A.
A squared equals A.
Sorry.
Yeah, it's not 2A equals 0, that follows.
Since you have interferences as essential ingredient, that also ties it up with complex numbers.
You might think so, but in fact, interference will be there if you have even negative numbers. So like in the three-slit experiment I'll mention in a second, I'll only put, which illustrates all the, in some sense, all the antinomies or the paradoxes of quantum mechanics, just with three-slit diffraction. You only need to look at amplitudes of +1 and -1. So what's absolutely crucial is to have negative amplitudes. But why you need complex, I'm not, again, you know.
In fact, it's sort of an extra thing that one has to, that it's not sufficient just to stop at the level of interference down.
I just have a clarification. Omega is the sample space and A is the algebra that is formed by all the events, right? Events in the sample space. So what is that A square equal to A? What
that's for an element. So I should actually, I was calling them E usually. So that's right. So I should, let me see. So for all, I'll call it, go back to call it E. For all E's in the event algebra A, so if we're just thinking of the algebra, let's not worry where it came from. Just, then it happens that E times E equals E. That's a property of the Boolean algebra. You can see that easily because I erased it again, unfortunately, but the intersection of two, remember the intersection of two events, the product of two events is, in set theoretically, is the intersection. So if you intersect the set with itself, of course you get back the same set. So that's in that case obvious that that's true. But what's not so obvious is that all the properties of being a Boolean algebra follow from this one axiom. Okay, so the dynamics comes in. So this is all kinematics. The dynamics is meant to come from the path integral or something closely related to the path integral, and that's what we call the quantum measure. Just as a classical probability measure gives you attaches a probability of positive real number between 0 and 1 to every event, we will here this quantum measure will attach a positive real number to every event too, but only in certain very special cases will it be able to be interpreted as a probability. So we'll come back to this, but let me make a claim. a very strong claim is that anything you can compute using any other formulation of quantum dynamics, you can compute with the path integral. So if you want the outcome of any experiment, you can compute that just using the path integral and never mentioning these other objects like POVMs or Schrödinger equation or state vectors. So
what is this specific claim about? Like, you're saying that all...
well, this is at the moment metaphysics. I mean, I don't want to turn it into a theorem. It's just the claim is that you can compute everything that you would compute in any other way. With the path integral. It's not a precise claim. In some cases, you'll do it more easily with the path integral. In some cases, it may become harder with the path integral. But I'm just saying that to give the sense, just to emphasize that we want to start with this quantum measure and nothing else, and that's going to be the dynamic. So let me give an example. Now let me try and make a more concrete example. Of such a computation, which I don't think you'll find anything surprising, but it illustrates a history's way of thinking about processes, quantum processes. So this will be interferometry. So I want to remind you of something about the path integral. So every path, every element of history, every history, more generally, has an amplitude which, for reasons that we don't fully understand, is a complex number in general. And and also I'm going to bypass something which is, in full generality, you want to attach amplitudes not to individual histories, but to pairs of histories. This is related to what's called the decoherence functional, say gamma 1, gamma 2. But it's just it's a small technical development of the path integral, which you're forced to do in general. It's related to what people call the Schwinger-Keldysh way of talking about quantum mechanics, for those who are familiar with it. And then I want to say for every event, so every element in the event algebra, every subset, it has a measure. And remember, the events are just sets of histories, and so that measure is computed in a way that you know very well. It's computed from the individual histories. Basically, at the cost of a slight oversimplification, you just take the amplitudes and add them up in squares, and that gives you the measure. And then all the cases that we'll look at, that'll be literally true, but one should be aware that there are more general cases where the definition is a little bit more involved, and it refers to these pairs of histories. Okay, so let's look at this, keeping this in mind, keeping this in mind, let's look at some sort of interferometry experiment. So I think this is called, I never can remember which interferometer is which, but I think this is called the Mach-Zehnder type of interferometry. So, and what it is, it's just a bunch of sort of empty spaces or beams or something, interrupted by beam splitters or beam mirrors or yeah.
The amplitude that is associated with every gamma is just a random variable. You have
Well, it's
a
not a
random
random.
variable for, so you call a random variable as an amplitude. And
No, I don't
that-
call it a random.
no. What is an amplitude?
Just a complex number. It's nothing but a complex number.
No.
It's a choice of dynamics.
Here, let me just talk for another 2 minutes and then ask your question again. Because we'll see explicitly here what are the complex numbers. Okay. So it's some sort of setup like this. You have some laser, say, nice, a single photon source, for example. It sends out a photon, and it reaches a beam splitter, and then it either reflects off, or it doesn't, or it goes through. If it goes through, it comes to another beam splitter, and then again it either reflects off, or it goes through, comes to another beam splitter, same thing, it's getting boring here. And then the fourth beam splitter, all the same story. At each one of them, it either goes through or it reflects off. Now, here we can see many possible histories. Let me give names to, what have I done? Yeah, to give names to these beam splitters. So this is one, I'll call it this number, 3, 4, and then
Equal transmission.
these outgoing beams, we have 5, 6, 7, okay, and 8. So now, what is the history in this situation? It's just a path, it's just one particular trajectory. So this, I hope, will also clarify the meaning of the way the word history is being used. It's just one particular trajectory that the photon might follow. So it might go here, 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 and here, for example. So let me consider the event 6. By the event 6, I mean, remember it's a question, so we're asking, does the photon emerge in beam 6? So that corresponds to a set of histories. What are those histories? So one of them might be 1, 2, 4, 6. So I'll write it like this. 1, 2, 4, 6. Means it comes here, it encounters the first beam splitter, it goes through, it reflects off the second beam splitter, going to 4, and it goes through again and it comes out at 6. So that's one way it could get here. But of course there's another way it could get here. It could first reflect here, and reflect here again, and that would be 1, 3, 4, 6. I hope. Yes. So these are these two events these two histories belong to the event E, which is, I called 6 for short. And each of them has an amplitude, and if we want the quantum measure of that event, which will work out in this case to be just the probability of a detector here finding the photon, if it's a perfectly good detector, then we just need to add up those two amplitudes and take the square. So what are the amplitudes of these events? Now I have to give you the rules for how these amplitudes, what happens, how you compute the amplitude of a history. So it's characteristic that the amplitudes of a given history is just a product of amplitude. There's a kind of locality here. It's just a product of amplitudes of the individual portions of the history. So if you break this history up into portions, well, first it freely propagated. Of course, first it was emitted by the laser. There's some amplitude associated with that, but it's the same for all the histories, so we're just not worry about it. Then there's an amplitude to propagate to here. Then there's an amplitude to be reflected or not to be, or to pass through. Then there's an amplitude, depending on which one it did, to propagate again. So the net amplitude is some sort of product. I don't know how to write it, but the beam splitter's amplitude times the propagation amplitude times beam splitter and so on. So the propagation is just something simple that we know. It's just moving freely. And the important thing here is that I've set it up like a square. So the propagation part of the amplitudes are the same for every history. So they will just come out in vector in front. So I'm going to ignore them in computing. It's only relative amplitudes in the that matter. So the important things are what happens at the beam splitter. So now what does happen? What is a beam splitter? Mathematically, it's a device or kind of object, whatever. Well, it's a mirror basically. So which has a certain amplitude for the particle to be transmitted and a certain amplitude for the particle to be reflected. And by an appropriate phase convention, you can always choose them like this. This is a consequence of the unitarity of the scattering at the beam splitter. You can always choose it so that the amplitude for transmission is 1 and the amplitude for reflection is the square root of -1. If you want to, which I will not worry about, normalize them, then you may want to put a 1 over square root of 2 in each one of those places. But the important thing is that the relative phase is 1 and I for a reflection. So we're doing this just as a sort of practice. How does the path integral work? How do we get the quantum measure of this particular event emerging into 6-beam? Well, it consists of two histories, as we saw. This whole thing together is E. What are the amplitudes? So this one's at 1, 2, 4, 6, right? So it's this is this history. So what did it do? It went through, it propagated, ignore that, it went through, that's an amplitude of 1, propagated again, that's the same for all of them. Here it bounced off, so that's an amplitude of I, and then it went through again. So the amplitude in that case is just 1 times I times 1, which is equal to I, right? On the other hand, let's look at this other one.
So the event will correspond to processes which start at 1 and end at 6, is it?
That's all, yes. Yes, right, that's one. So the other one follows this path. Maybe I should call them gamma 1 and gamma 2, or should have called them alpha and beta or something. Anyway, so this is 1, gamma 1, this is gamma 2. So what is it doing? Propagated, it reflected, that's a factor of I. Reflected again, that's a factor of I. Came here and it reflected again, that's another factor of I. So its amplitude is I times I, which is minus I. Okay, so the net amplitude in this case is 0. After all that work. So the net, so the quantum measure of this event, maybe I'll call it E sub 6. So that what we've computed here is the measure of E sub 6 is equal to 0. Yes.
So what is quantum measure? So you just add them and square it?
Yes.
Yeah. Okay.
That's all it is in this case. Yes.
So is it just like amplitude square, which is like probability? So it's all related to that?
Yes, that's exactly
Yeah,
right.
so that's
all it is. The only thing is that, as we'll see if we get far enough, is that you can't always interpret it as a probability precisely because it satisfies only the 3-slit sum rule and not the 2-slit sum rule. Okay, so let's do, I don't know how. Oops. Okay, let's do one other one that's not trivial. So let's look at the event E8. Let's redo this. I'll just redo everything with E8 now.
This is shown, so it's 3:30 now. People want to, there is tea outside, if we want to take a break and then come back in? Do you think maybe after your example?
Yeah, let me do the example and then,
Okay.
yeah, it will be, I was going to do another Mach Zehnder, but let's just finish this one. And then, so do one non-trivial computation. But what I want to say, before I do that one, I want to say that because we got 0, because the measure of E6 was, so on this port, mu is equal to 0, that means, from an operational point of view, that means if you put a detector here, you will get some counts, but only dark counts. Right? So if you put a detector here, you'll never get, if it was a perfect detector, you would never get anything. And in this in this whole philosophy or point of view on quantum mechanics, we go farther and we say the photon never goes here. Even if you don't put a detector here, it never goes here. So that's a key thing. It's called a principle. It's an assumption, a hypothesis about the microscopic world. It's called, this is trying to go where you would like quantum mechanics to go, right? To tell us something about the real world and not just about the measurements. So we're not just saying if you put a detector here, you won't get anything. We're saying the photon really never will go here. So an event which has, this is the key thing, an event, an event of measure 0 never happens.
So,
Whether or not we look for it.
so that's, Urvashi has a question.
Yeah, okay. It's this preclusion.
Yeah, I mean, the question is how do you know that?
How do I know?
How do you know that just because your amplitudes cancel, you are confident that even if I don't put a detector, I won't have it?
We don't know, right? So
We
this
don't.
is not, but we make this hypothesis, and that will, if we follow it out to its conclusion, then we can say quite a lot about the microscopic world. But it's absolutely a hypothesis. It could be wrong physically. But it's the most, it's the, let me say, it seems to me that if you believe that the quantum measure, which is ultimately just coming from the path integral, if you believe that it's telling us anything at all about the world, then I don't see how you can escape this fact. But you could believe it's just not telling us anything about the world. Someone expressed that point of view. You could say it's just an algorithm for knowing what detectors will do. And then, if you want to know about the world, you either say, as some people say, shut up and calculate, and you don't ask, or you say, it's something totally different, who knows. But this is an attempt to say that it's not totally different. It's as close as it could have been and still be a realistic.
But Rafael, why is detection not reality?
Oh, that is a reality.
That is it.
That is reality.
Yeah.
But you asked me, how do I know
It's
that if
not the
I...
only reality.
That's the important thing.
Yes. And it's a derived reality.
No, but
the detector is not the most basic thing of reality. It's a very complicated system made of wires and
But it's okay.
electronics, and it's all built out of atoms ultimately. That's the reality. That's the point of view. The detector is a secondary object. It's real, it's perfectly real, but it's not more real than the objects on which it's built.
each history, they even have to end at the same point.
No, they don't. That's why I made this little that's why I mentioned about really neat pairs of histories and so on.
How does
In
one
the
know-
examples that I'll be using, which I don't know how many I will get, I'm limited to them where the histories all will end at a single point, and then we don't have to worry about this further complications. So the general statement is that histories which end at different points will not interfere with each other. Histories that end at the same point will. In particle physics, it's known, it has a name of inclusive cross-section, or I forget what the opposite is. You know, if you want the inclusive cross-section, you have to sum the individual cross-sections. You don't add the amplitudes first and square, you square first and add the amplitude. So the general statement is that the quantum measure is some combination of adding the amplitude, squaring, and then adding again. But for it doesn't, I don't think that adds anything to the basic understanding of the setup. So I'm going to.
I'm a little bit confused. So, how is this different from a discretization of standard path integral? I mean, the measure.
This is meant to be the standard path integral.
Yeah.
I don't know what you mean by discretization.
In the sense that, like, if you had like an assignment of weights for each trajectory, I mean, isn't that this is what would come out?
That
right?
is,
This-
like he said, the transmission is the same in all cases, so that continuum doesn't have to be, it comes out as an overall factor here.
This is propagation example.
Sorry, I didn't get you.
Yeah, the real amplitude is not just I.
Uh-huh.
It's I times the amplitude to propagate from the laser to the first beam splitter, times
That's
the
right.
amplitude to propagate from the first beam splitter to the second, times this. So that if I introduce this sort of P, I don't know what to call it, some P representing the propagation amplitude, there'd be one, well, I'll put one here. P, P,
No, that's fine.
P.
Yeah.
So I would have to put in an
That's right.
overall P
Right. I
cubed
mean, if you
or
put that in,
something.
it will be but I'm saying that will just be the evolution of standard quantum mechanics in the path integral language, wouldn't it?
Yes.
So
All I'm trying to do is illustrate the standard path integral
okay.
in a simple setting.
But then also, but you're also
I mean, of course,
one step further by saying, now making a
But
statement.
now I've made a statement about the real world that some people would not attribute to the
Yeah,
present.
but it looks like that the photon knows what is going to happen with him in the future and he's not going there where his amplitude will be cancelling out. It's like entanglement time kind of thing happening.
No, but
Yeah,
but in the simple
that's it's
No,
not like
but-
that's the mystery of quantum mechanics. How does it know?
That it will be zero.
I mean, if you think of it classically, it either follows this path or this path. If it follows this path, how the hell does it know that the other beam splitter was there at all? That is somehow the mystery of quantum
Can
mechanics.
I add?
And in fact, it'll force us to say that reality is not represented by a
But,
single
but,
mystery.
but so suppose one just follows the standard double slit event, the wave function, and does not go into this sophisticated picture. There
This
you
is
have
not
the example
sophisticated.
of, yeah, I know, but the example of destructive interference. If you
Yes.
just stick to the wave function
Yes.
description you get, and that has the same spirit as this one. That one can say that the points where the probability is zero is the event where you will never find the particle. So
Well, you said that you'll never find the particle. but
Yeah,
I'm
yeah,
going further
you-
and saying the particle doesn't go
Doesn't
there.
exist.
it doesn't. So there is some ontological aspect you are adding there, or would you say
Yes.
that's more epistemological statement and
No.
of not
If you-
finding
if
it
If you
here?
force me to use that language, I'll say it's ontological. It's ontological.
So that's the basic difference. Otherwise,
So Purna
Yeah.
had-
Well, remember I said I wanted to do three things. I wanted to introduce history's formalism, which is the standard, absolute standard path integral. Then I wanted to talk about possible generalizations. I guess I won't get to that. And then I wanted to talk about the deeper meaning. What is this formalism telling us about reality? We haven't got to the third one yet, but in the third, except this is the basis of that third.
So you're taking it as literally true.
I'm taking
The-
I'm taking that this measure tells us something about reality, independent of any observers or instruments that might be there or might not be there. And this is the sort of minimal program, the minimal requirement that you seem forced to adopt if you believe that this quantum measure, which is just basically the path integral, tells us anything at all about the deep reality, about the actual microscopic reality.
I was just wondering if there's a way of understanding this deeper notion of reality, devoid of a detector.
Well, let's put that off to of course, if there's not, then the whole thing is a failure. We want to be able to, if we're doing quantum gravity, then where is quantum gravity interesting? Well, I would claim that in connection with the cosmological constant, we're seeing something about quantum gravity. But more generally, you expect it to be you expect to see the true quantum gravity regime either at length scales of 10 to the minus 32 centimeters, which is out of reach for a century at least, or in the early universe. And in both of those regimes, we don't have detectors of the size of 10 to the minus 32 centimeters. And we certainly don't have observers and detectors and so on in laboratories in the early universe. So we're talking about regimes or realms in which the operational way of thinking about quantum mechanics doesn't serve. And so the practical, if you can call it practical motivation for something like this, is to be able to think about quantum gravity. The philosophical motivation is, even if you're not interested in quantum gravity, many people have been unhappy with quantum mechanics right from the very beginning. And why are they unhappy? Because of the same thing that Sadiq, I think, said, that it seems that it's come down to us, it's only telling us about what instruments we'll find under certain conditions, and it's not telling us what's really going on in the world, why are the instruments are doing this, and so on. So that's the philosophical motivation. And so this is an approach to resolving those issues.
Bal had a question.
Okay.
Sorry, I'm going
No,
to be trying to make sure everybody gets
You should
into the.
stand up so that people can see you. No?
There are two questions. First, I will ask them more. Suppose I take a quantum field, standard local quantum field theory.
Okay.
Take a space-time region.
Yes.